What we really want is the concentration of the potassium hydroxide or the hydroxide ion, but we were given the pH of the solution. So if we do the calculation of 10 to the minus pH, then what we get is the concentration of the hydronium ion. So that is not what we want. In fact, what we want is the concentration of the hydroxide ion. So we need to do 10 to the minus POH instead of 10 to the minus pH. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 8.1 to 8.3. As you can see on this slide, these topics fall under Unit 8 in the AP Chemistry curriculum, Acids and Bases. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 8.1, Introduction to Acids and Bases. Here are some essential knowledge statements from the AP Chemistry course and exam description. The concentrations of hydronium ion and hydroxide ion are often reported as pH and POH respectively. And these equations are listed on the AP Chemistry equations and constant sheet. So what you're looking at is actually page 2 of the equation sheet, and there is a section entitled Equilibrium. Now, the first 2 equations that are listed in this section were actually included in Unit 7, entitled Equilibrium, but all of the rest of the equations in this section refer to Unit 8, Acids and Bases. So there is the definition of pH. It is equal to the negative log of the concentration of the hydronium ion. And then the definition of POH is the negative log of the concentration of the hydroxide ion. The terms hydrogen ion and hydronium ion and the symbols H plus and H3O plus are often used interchangeably for the aqueous ion of hydrogen. Hydronium ion and H3O plus are preferred, but H plus is also accepted on the AP exam. Water autoionizes with an equilibrium constant that is referred to as Kw. And again, you can see this particular equation on the equation sheet. The Kw, the equilibrium constant for the autoionization of water, is equal to the concentration of the hydronium ion times the concentration of the hydroxide ion, and at 25 degrees Celsius, that is equal to 1 times 10 to the negative 14. In pure water, pH is equal to POH. Pure water is called a neutral solution, and at 25 degrees Celsius, the negative log of the Kw, which is known as the pKw, is equal to 14, and thus pH equals POH, which equals 7. Again, that's at 25 degrees Celsius. So that equation also listed on the AP Chemistry equations and constant sheet in the section entitled Equilibrium. And the value of Kw is temperature dependent. So the pH of pure neutral water will deviate from 7.0 at temperatures other than 25 degrees Celsius. Now let's move on to the practice for topic 8.1. This is question 1. Question 1 says the following. The pH of pure water at 10 degrees Celsius is 7.27. Which of the following provides correct predictions for the POH of pure water at 10 degrees Celsius and the value of pKw at 10 degrees Celsius? So the first thing I will focus on is the fact that this is a sample of pure water. So in pure water, pH equals pOH no matter what the temperature is. So the fact that the pH of pure water happens to be 7.27 at this temperature, and it is a sample of pure water, then the pOH must also equal 7.27. So looking at our four choices, the pOH of pure water at 10 degrees Celsius is equal to 7.27, which means that the correct answer to question 1 is either choice C or D. Let's go ahead and eliminate choices A and B. Now I'd like to focus on the fact that we are not at 25 degrees Celsius. So the value of kW is temperature dependent. So while the value of pKW is equal to 14 when the temperature is 25 degrees Celsius, if the temperature changes from 25 degrees Celsius to a different temperature, then the value of kW and pKW will change. So we know that the value of pKW at 10 degrees will be some number other than 14. In fact, it will be the sum of pH plus pOH, so 7.27 plus 7.27 is 14.54. So the correct answer to question 1 is choice D. The pOH of pure water at 10 degrees Celsius is equal to 7.27, and the value of pKW at 10 degrees Celsius is greater than 14. All right, well, hopefully those answers and explanations make sense to you. Now let's go ahead and take a look at question 2. In question 2, it says that the pH of a 200.0 milliliter sample of aqueous sodium hydroxide in a beaker is recorded as 7.90. And then at the end of this question, it says, assume that the temperature of the solution remains constant at 25 degrees Celsius. Now, it turns out that sodium hydroxide happens to be an example of a strong base, but we will talk more about strong acids and strong bases in topic 8.2 in this lesson. So for right now, I'd just like to focus on the fact that we know the pH, and remember that on the equation sheet, we can relate the pH to the pOH. So therefore, what do I know about the pOH of the solution if the pH is equal to 7.90? Well, 14 minus 7.90, that will give me the value of the pOH, and that works out to be 6.10. Okay, well, now that I know the pH and the pOH of the solution in this beaker, I can also use these equations from the equation sheet to relate the pH to the concentration of the hydronium ion, and I can relate the pOH to the concentration of the hydroxide ion. So I will pick up my calculator, and I will take 10 to the minus 7.9, and when I do that math, the concentration of the hydronium ion works out to be 1.3 times 10 to the negative 8 moles per liter. I will go ahead and do a similar calculation to determine the concentration of the hydroxide ion. So I will pick up my calculator and do 10 to the minus 6.1, and when I do that math, I get 7.9 times 10 to the negative 7, and that is the concentration or the molarity of the hydroxide ion. Now note that this is a base, so this is sodium hydroxide. Therefore, the pH is greater than 7. What would happen if the pH were eventually equal to 7 is that these two concentrations, hydroxide and hydronium, would be equal. But you can see that right now, the concentration of the hydroxide ion happens to be greater than the concentration of the hydronium ion. So what if we had added an excess amount of water to this beaker? Well, eventually, if we added so much water that we kept diluting and diluting this solution, the pH would approach 7. So this is the question that we have to answer. Which of the following correctly predicts how the pH of the solution and the value of the concentration of the hydronium ion in the solution will be affected by the addition of distilled water to the beaker? So under this extreme example, what if we added so much water that the pH equals 7? If the pH of the solution equals 7, then the concentration of the hydronium ion would equal 1 times 10 to the negative 7 molar, and also the concentration of the hydroxide ion would be the same value. But I'm going to focus my attention on the hydronium ion because that's what we need to answer for question 2. So the concentration of the hydronium ion will increase as the pH decreases. Now, if you're having a hard time seeing how can the concentration of the hydronium ion increase because we're not actually adding an acid, we're just adding water, take a look at these two values. Which is bigger, 1.3 times 10 to the negative 8 or 1 times 10 to the negative 7? Well, 1 times 10 to the negative 7 is a larger value, so as the pH decreases, the concentration of the hydronium ion increases. Now, let's say we went to 7.8 or 7.7 or 7.6 for our pH if distilled water is added. What would happen to the concentration of the hydronium ion? 10 to the negative 7.8, 10 to the negative 7.7, 10 to the negative 7.6. If you do that on your calculator, this is what happens. 1.3 times 10 to the negative 8. Now that becomes 1.6 times 10 to the negative 8. Now it becomes 2 times 10 to the negative 8. Now it becomes 2.5 times 10 to the negative 8. So we are now answering this question. So the answer to question 2 is the pH should decrease as distilled water is added to this beaker, and the concentration of the hydronium ion will increase as distilled water is added. So the correct answer to question 2 is choice B. The pH decreases and the concentration of the hydronium ion increases when distilled water is added to this beaker. All right, well, hopefully those answers and explanations make sense to you. Now it's time to take a look at question 3 in this packet. In question 3, it says, a beaker contains a 100.0 milliliter sample of nitric acid, which has the chemical formula HNO3, and the pH is 5.25. Distilled water is added to the beaker until the final volume of the solution is 500 milliliters. Assume constant temperature at 25 degrees Celsius. Now, in question 2, we had an example of a strong base, and that was sodium hydroxide, NaOH. Here, in this question, we have an example of a strong acid, nitric acid, HNO3. You don't really have to know anything about strong acids or strong bases to answer question 2 or question 3 in this packet, but in this lesson, we will go ahead and take a look at topic 8.2 coming up, and that would be examples of strong acids and strong bases. So that's coming up in topic 8.2. Now, for this question, part A says, calculate the value of the concentration of the hydronium ion in the 100 milliliter sample of nitric acid present in the beaker at the beginning of the experiment. So if we know that the pH is 5.25, and we know how to use this particular equation, that would be 10 to the minus pH will give us the concentration of the hydronium ion in that beaker. So when I pick up my calculator and I do 10 to the minus 5.25, I get 5.6 times 10 to the negative 6 moles per liter. So that is the concentration of the hydronium ion, and that is the answer to part A. Now it does say in this experiment that distilled water is added to the beaker until the final volume of the solution is 500 milliliters. So it looks like in question 2 and in question 3 in this packet, we're doing a dilution with water, and it's affecting the pH and also changing the concentration of either the hydronium ion or the hydroxide ion, depending on what we're considering in this example. So we're going to focus our attention on the new pH. So part B, calculate the pH of the 500 milliliter sample of solution present in the beaker at the end of the experiment. And so an easy way to do the calculation in part B is to use something I have mentioned in earlier episodes of AP Chemistry Review and Practice, the dilution equation involving molarity times volume. And then when water is added, you have a new molarity and a new volume. And the volume could either be in milliliters or in liters as long as they have the same unit on both sides of the equation. So M times V equals M times V. We know that the molarity of the hydronium ion from our answer to part A is 5.6 times 10 to the negative 6 moles per liter. And that was before the additional distilled water was added. So the volume was 100 milliliters. The new molarity of the hydronium ion is a number that we don't know yet, but the new volume is now 500 milliliters. So hopefully you can see that really all you have to do is solve for the new concentration, and then take the negative log of that value to get the pH. So if you take 5.6 times 10 to the negative 6 and essentially divide by 5 based on this 1:5 dilution with water, then the new concentration of the hydronium ion works out to be 1.1 times 10 to the negative 6 moles per liter. Now, that's not the answer to part B. We still have to take the negative log of the concentration of the hydronium ion. And when we do that, to get the pH, I would predict that the pH is going to be still less than 7, but it's going to be greater than 5.25. So when we do this math, we get 5.96 for the pH of the solution that is present in the beaker at the end of this experiment. Now, some of you watching this video might wonder, how do we round off our answers in terms of the rules for significant figures? I do present in my video for topics 8.1 to 8.3 in my YouTube playlist that's organized by AP Chemistry CED units, a detailed explanation of how the significant figures and the rules for sig figs apply with pHs. But I will go ahead and tell you that had you rounded off your answer for part A to, let's say, a slightly extra number of significant figures, so for example 5.62 times 10 to the negative 6 molar, if that were your answer to part A, then when you did the math for the dilution in part B, you would have gotten a slightly different pH. So I'm writing down 1.12 times 10 to the negative 6 for my concentration of the hydronium ion that's present in the beaker at the end of the experiment. And when I took the negative log of that value, I got 5.95. So the answer to part A of question 3 is approximately 5.6 times 10 to the negative 6. And the pH in part B is approximately 5.95 or possibly 5.96. All right, well, the first 3 questions in this lesson, in this packet, relate to topic 8.1. So now it's time to move on to the review for topic 8.2, pH and pOH of strong acids and bases. Here are some essential knowledge statements from the AP Chemistry course and exam description. Molecules of a strong acid, and here are 6 strong acids that you should be familiar with on the AP Chemistry exam: hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, HI, perchloric acid, HClO4, sulfuric acid, H2SO4, and nitric acid, HNO3. These 6 strong acids are examples of acids that completely ionize in aqueous solution, so 100% ionized, to produce hydronium ions and the conjugate base of the acid. The concentration of the hydronium ion in a strong acid solution is equal to the initial concentration of the strong acid. The pH of the strong acid solution is easily calculated. Now, what about strong bases? When dissolved in solution, strong bases, for example, group 1 and group 2 hydroxides, completely dissociate to produce hydroxide ions. Now, the concentration of the hydroxide ion in a strong base solution is equal to, and you can see on this slide, these are examples of typical charges on monoatomic ions in ionic compounds, but let's focus our attention on the first 2 groups, or the first 2 columns. So group 1 contains the alkali metals, lithium, sodium, potassium, rubidium, cesium, francium, and that would be +1. So the chemical formula of lithium hydroxide is LiOH. The chemical formula of sodium hydroxide is NaOH. The chemical formula of potassium hydroxide is KOH. So if we know that we have a group 1 hydroxide, then the concentration of hydroxide is equal to the initial concentration of that substance. So for example, if you have a 0.020 molar solution of sodium hydroxide, then the concentration of the hydroxide ion is that same number, 0.020 molar as an example. Well, what about group 2 hydroxides? As you can see, group 2, that's located here. These are called the alkaline earth metals on the periodic table. So we have examples such as magnesium and calcium and strontium. You can see that there's a 1:2 ratio for that formula of that group 2 hydroxide. So there's magnesium hydroxide, there's calcium hydroxide, strontium hydroxide. So if I have a 0.020 molar solution of something such as barium hydroxide, which is a group 2 hydroxide, then the actual concentration of the hydroxide ion would be twice as much as that concentration. So 0.040 molar would be the concentration of the hydroxide ion in that solution. So again, now that we know that we have information about topic 8.2, and the last essential knowledge statement says that the pOH and the pH of the strong base solution is easily calculated. Again, these were the equations that I mentioned earlier in this lesson. So now it's time to move on to the practice for topic 8.2. This is question 4. In question 4, we are given a table and it says, fill in the missing information in the table above. In the space below, show the setup for the calculations that are required to determine the missing information in each row of the table. Assume that each solution is at 25 degrees Celsius. Now, these are both strong acids in this table. We have nitric acid, which is HNO3, and then we have hydrochloric acid, HCl. So for this first part, we have to determine the concentration of the hydronium ion as well as the pH, and we have a 2.3 times 10 to the negative 4 molar solution of nitric acid. So since nitric acid is a strong acid, the concentration of the hydronium ion in a strong acid solution is equal to the initial concentration of the strong acid. So I haven't done any calculations yet. I just simply wrote that same number, 2.3 times 10 to the negative 4, as the molarity of the hydronium ion, because nitric acid is a strong acid. Now, I will need to set up a calculation to determine the pH, and that would be the negative log of the concentration of the hydronium ion. So when I pick up my calculator and I do the negative log of 2.3 times 10 to the negative 4, I get a pH of 3.64. So that is the missing information in row A of the table. Now, with row B of the table, we don't know the concentration of the hydrochloric acid, but we are given the pH. So now it's going to be 10 to the minus 5.77, and then that number, 10 to the minus 5.77 on my calculator, is not only the concentration of the hydronium ion, but that is also the concentration of the HCl. So 1.7 times 10 to the negative 6 molar is the concentration of the hydronium ion. Well, now that that table is complete, let's go ahead and move on to our next question in the packet. This is question 5. It involves a strong base, and it's a multiple choice question. In question 5, we are told that the pH of a solution of a strong base, potassium hydroxide, which has the formula KOH, that the pH of that solution is 8.00. The concentration of KOH in this solution is closest to which of the following? Now, here is an important piece of advice for anyone who is planning to take the AP Chemistry exam. Be careful and watch out for this common mistake, and that is, you might be thinking, all I have to do, if I'm given the pH, is to do 10 to the minus pH, and that will get me the concentration I'm looking for. Well, 10 to the minus 8 is not the correct answer to question 5, and here's why. There is an important distinction between the concentration of the hydronium ion and the concentration of the hydroxide ion. There is an important distinction between the pH and the pOH. So if we go back and look at this question, we're talking about a strong base. What we really want is the concentration of the potassium hydroxide or the hydroxide ion, but we were given the pH of the solution. So if we do the calculation of 10 to the minus pH, then what we get is the concentration of the hydronium ion. So that is not what we want. In fact, what we want is the concentration of the hydroxide ion. So we need to do 10 to the minus pOH instead of 10 to the minus pH. So what is the pOH? In this case, that would be 14 minus 8. So if the pH is 8, the pOH is 14 minus 8, or 6. Now, the concentration of the hydroxide ion is 10 to the minus 6. And based on the fact that potassium hydroxide is an example of a group 1 hydroxide, if we know that the concentration of the hydroxide ion is 1 times 10 to the negative 6 molar, then that means that the concentration of potassium hydroxide is also 1 times 10 to the negative 6 molar. So again, the correct answer to question 5 is not choice A, but rather choice B, because what we had to do is calculate the pOH and then do 10 to the minus pOH to determine the concentration of the hydroxide ion and the concentration of KOH. So hopefully that explanation makes sense. Now let's move on to question 6. This also involves a strong base, but this is a group 2 hydroxide. So we have a slightly different calculation. So question 6 says the following. A student performs the following calculation to determine the pH of 0.050 molar barium hydroxide. So we can see the student's calculations, and they got a pH of 12.70. And it says, identify the specific mistake that was made by the student in this calculation and determine the correct value for the pH of 0.050 molar barium hydroxide. So with a group 2 hydroxide, then the concentration of the hydroxide in that solution is twice as much as the concentration of that group 2 hydroxide. So we have 0.050 molar barium hydroxide, but if we multiply by 2, then the concentration of the hydroxide ion is actually 0.10 molar. So the student's mistake was that they did not account for the fact that for every 1 mole of barium hydroxide in solution, there's actually 2 moles of the hydroxide ion in solution. So now let's go ahead and finish the calculation. So we're going to take the negative log of the concentration of the hydroxide ion, and that will get us the pOH. So the negative log of 0.10 molar is 1. And then 14 minus the pOH gives us the pH. So 14 minus 1 is 13. So you can see that the correct pH is actually 13, not 12.70. And the reason that I wrote question 6 is to remind you that there is a difference between a group 1 hydroxide and a group 2 hydroxide. So just be careful that you don't make this particular mistake on the AP Chemistry exam. All right, well now let's move on to question 7. Question 7 involves a strong acid. It also involves a weak acid. So question 7 will be a nice transition from topic 8.2, the pH and the pOH of strong acids and bases, to topic 8.3, where it has to do with weak acids and bases. So let's go ahead and take a look at the details of question 7. It says that the pH of solutions of 2 different acids prepared at 2 different concentrations were measured and recorded in the tables above. Use the information listed above to answer the following questions. Part A, perform a calculation to illustrate why HClO4, which is perchloric acid, is classified as a strong acid. So remember that with strong acids, they are completely ionized in aqueous solution. So the concentration of the hydronium ion in a strong acid solution is equal to the initial concentration of the strong acid. So what is the negative log of 0.01? Again, the negative log of 0.01 is equal to 2. What is the negative log of 0.1? That would be 1. So we can see that these calculations show that the concentration of perchloric acid is the same as the concentration of the hydronium ion in solution. So therefore, perchloric acid must be 100% ionized in aqueous solution, because taking the negative log of the concentration of the acid gives us the pH. Now you'll notice that in the table on the right side, that is a weak acid. And the reason why you can tell it's a weak acid is because the pH is slightly higher for an acid of that same concentration. So let's go ahead and move on to part B, which is actually a weak acid. It says, determine the percent ionization of HClO2 in a solution of 0.10 molar HClO2, which is called chlorous acid. So why is it going to be less than 100%? Because not all of that acid completely ionizes in solution. So let's go ahead and take a look at the details. We have the chlorous acid, HClO2, reacting with water to produce the hydronium ion, and then its conjugate base, which is ClO2-, or the chlorite ion. And I'm using the double arrows to indicate an equilibrium situation. So we know that this reaction does not go all the way to completion, because HClO2 is not on your list of strong acids, and we can tell that the pH of 0.10 molar chlorous acid is slightly higher than 1. So if I start with a 0.10 molar solution of HClO2, I do not get 0.10 molar hydronium ion in solution because it doesn't ionize all the way. So the concentration of the hydronium ion in this solution is less than 0.10 molar. And all we have to do is take 10 to the minus 1.55 to get the concentration of the hydronium ion. So 10 to the minus 1.55 gives us 0.028 molar for the concentration of the hydronium ion. Now, it's asking for percent ionization. And if you're watching this video and you haven't heard exactly what percent ionization is, it's coming up in topic 8.3 in just a moment. So in topic 8.3, which is entitled Weak Acid and Base Equilibria, the percent ionization has the following formula. So what I'm showing you on this slide is that a generic acid that has the chemical formula HA reacts with water to produce the hydronium ion and then its conjugate base, or A minus. The percent ionization is equal to a ratio and then times 100. So it's going to be the following ratio. What's the concentration of the hydronium ion in solution at equilibrium divided by the original concentration of the acid and then times 100. So if it were 100% ionized, then that ratio would be 1. But if it's not 100% ionized, then that ratio will be less than 1. So for perchloric acid, it would be 100% ionized, but for chlorous acid, or HClO2, it is less than 100% ionized. Let's go ahead and do the math. Concentration of hydronium divided by the initial concentration of the chlorous acid, HClO2. So that's going to be 0.028 molar, which is what we calculated when we did 10 to the minus pH, and then divided by the initial concentration of HClO2, which is 0.10 molar. And so when we do that math, we get that only 28% of that acid is ionized. So what we will see on the AP Chemistry exam is that a weak acid is only partially ionized in aqueous solution. So this will be a good transition to our next topic. So it's time to move on to the review for topic 8.3, Weak Acid and Base Equilibria. Here are some essential knowledge statements from the AP Chemistry course and exam description. Weak acids react with water to produce hydronium ions. However, only a small percentage of molecules of a weak acid will ionize in this way. Thus, the concentration of the hydronium ion is much less than the initial concentration of the molecular acid, and the vast majority of the acid molecules remain unionized. A solution of a weak acid involves an equilibrium between an unionized acid, which is denoted as HA on the equation sheet, and its conjugate base, which is denoted as A minus on the equation sheet. And so the equilibrium constant for this reaction is Ka, often reported as the negative log of the Ka, or the pKa. And the pH of a weak acid solution can be determined from the initial acid concentration and the pKa. So this set of equations is listed on the AP Chemistry equations and constant sheet. So again, we're looking at weak acids. Now let's talk about weak bases. Weak bases react with water to produce hydroxide ions in solution. However, ordinarily just a small percentage of the molecules of a weak base in solution will ionize in this way. Thus, the concentration of the hydroxide ion in the solution does not equal the initial concentration of the base, and the vast majority of the base molecules remain unionized. A solution of a weak base involves an equilibrium between an unionized base, which is denoted as a capital B on the equation sheet, and its conjugate acid, which is denoted as Hb plus on the equation sheet. The equilibrium constant for this reaction is Kb, often reported as the negative log of Kb, or pKb. And the pH of a weak base solution can be determined from the initial base concentration and the pKb. So again, these two equations appear right next to the weak acid equations on the AP Chemistry equation sheet. There are two more equations mentioned in topic 8.3. The percent ionization of a weak acid or base can be calculated from its pKa or its pKb and the initial concentration of the acid or the base. The percent ionization can also be calculated from the initial concentration of the acid or base and the equilibrium concentration of any of the species in the equilibrium expression. Now, at the end of this lesson, when we get to the section entitled Advice to Help You Avoid Common Mistakes, I will go through lots of calculations where I can help you determine, do I know the pH or the initial concentration of the weak acid or the base or the Ka or the Kb. So at the end of this lesson, you'll see many more examples of calculations involving weak acids and weak bases. Finally, for any conjugate acid-base pair, the acid ionization constant and the base ionization constant are related by Kw. So these two equations are also listed on the AP Chemistry equations and constant sheet. All right, well, now it's time to move on to the practice for topic 8.3. This is question 8, which is a multiple choice question. Question 8 says the following. The reaction of the weak base pyridine, which has the chemical formula C5H5N, with water is represented by the equation above. So we can see on the left side of the equation, we have the formula for the weak base pyridine, and it's reacting with water. And on the right side of the equation, we can see what is known as the conjugate acid of pyridine. So that would be C5H5NH+. And then we also see the hydroxide ion. So this is the reaction of a weak base, and the Kb is unknown. In fact, that's what we're trying to find here in question 8. So it goes on to say, a 0.10 molar solution of pyridine has a pH equal to 9.11. Now the ionization constant Kb of pyridine is closest to which of the following values? So on the equation sheet, that is the equation for Kb. There's the generic representation of a weak base as capital B, and the generic representation of its conjugate acid as Hb+. So I'm going to go ahead and transform that generic equation to the specific details in this equation for pyridine. So I will replace the capital B with C5H5N, the formula of pyridine, and then in the numerator, I will replace Hb+ with the formula of the conjugate acid. It's known as the pyridinium ion, which has the formula C5H5NH+. All right, now what do we know in terms of plugging in numbers into this expression so we can answer question 8? Well, we are told that there is a 0.10 molar solution of pyridine, so I will put 0.10 molar on the denominator of this expression. And now for the numerator. I would love to know the concentration of the hydroxide ion. And we are given the pH, but be careful. Remember back in question 5 of this lesson, if you're given the pH and you do 10 to the minus pH, you're not going to get the hydroxide ion, you're going to get the hydronium ion. So what we really need is the hydroxide ion. And that's not 10 to the minus pH, but rather 10 to the minus POH. So how do we get the POH if we're given the pH? Well, that would be 14 minus the pH. So what's 14 minus 9.11? That works out to be 4.89. Now I could do 10 to the minus 4.89, and that will give me the concentration of the hydroxide ion. So 10 to the minus 4.89 is 1.3 times 10 to the negative 5. And it turns out that on the right side of the equation, based on the stoichiometry and the 1-to-1 mole ratio, not only is 1.3 times 10 to the negative 5 the concentration of the hydroxide ion, it's also the concentration of that conjugate acid or the pyridinium ion, C5H5NH+. At this point, we're basically done, and we could go ahead and just put these numbers into our calculator and determine the correct answer to question 8. But I'm going to take a quick pause in solving this question and remind you of something that I had presented in earlier lessons, earlier episodes of AP Chemistry Review and Practice. Do you remember back in Unit 7, which is entitled Equilibrium, the use of a rice table? I'm going to go ahead and use a rice table here in question 8 just to show you how you can track the information that we were given. So what was the initial concentration of the weak base pyridine? 0.10 molar. Do I care at all about a pure liquid? And therefore, do I need to know about the concentration of something such as water? No. So I'm going to ignore the information about water because it doesn't appear in the Kb expression and there is no concentration to worry about. Well, let's pretend that this reaction between pyridine and water has not yet occurred. So those concentrations on the right side of the equation would be 0, as in the reaction has not occurred yet. Now, technically in pure water, the concentration of hydroxide is actually 10 to the minus 7. But since 10 to the minus 7 is a really, really small number, I'm going to assume that there's no additional source of hydroxide from the reaction of this weak base in water. All right, well, now we get to the change row of the rice table. Normally, it would be in terms of x. So I see coefficients of 1, 1, 1, and 1. So it's going to be minus x for the change in pyridine. And it's going to be plus x for the changes of the pyridinium ion and the hydroxide ion. So now at equilibrium, I would have 0.10 minus x, x, and x. Let's go back to the information from question 8. We were given the pH. And since pH is not the same as pOH, I had to do 14 minus 9.11, and I got 4.89 for the pOH. Then I did 10 to the minus 4.89, and then that number, 1.3 times 10 to the negative 5 molar, is the concentration of the hydroxide, and that's present at equilibrium. So I put that in the bottom row of my right table. And then based on that 1-to-1 ratio, that number is also the concentration of the pyridinium ion, C5H5NH+. And now if you pick up your calculator and you do 0.1 minus 1.3 times 10 to the negative 5, what you will get is a number that is practically the same as 0.1. It's technically 0.0999887. So for our purposes, we can assume that 0.1 minus x is equal to 0.1. So I created this rice table in this part of the lesson to answer question 8, just to show you that a rice table can be very useful when you're solving reactions, problems involving weak acids and weak bases. So I will take these numbers from the bottom row of the rice table and put them into the Kb expression. And when I put those numbers into the Kb expression, 1.3 times 10 to the negative 5 times 1.3 times 10 to the negative 5 divided by 0.1, then this is what I got on my calculator. 1.7 times 10 to the negative 9. So we have now answered question 8. So what's the Kb, or the ionization constant for pyridine? It's choice C, 1.7 times 10 to the negative 9. Now you will see me mention rice tables in questions 9, 10, and 11 in this packet. So again, a rice table can be useful when you're working with weak acids and weak bases. Hopefully the answer to question 8 makes sense to you. Now, let's go ahead and take a look at question 9. Question 9 is actually very similar in setup to question 4 earlier in this lesson, but in question 4, those were examples of strong acids. So here in question 9, we have examples of weak acids. Question 9 says the following: fill in the missing information in each row of the table above. In the space below, show the setup for the calculations required to determine the missing information in each row of the table. Assume that each solution is at 25 degrees Celsius. So there is in row A only one thing that we don't know, and that is the initial concentration of this weak acid. So there is the Ka expression from the equation sheet. I will show you both the generic formula for a weak acid, which is HA, and then I'll substitute HA for the specific chemical formula, which is HC3H5O2, that is known as propanoic acid. So there's propanoic acid, HC3H5O2, reacting with water, and it produces the hydronium ion along with its conjugate base, which is the propanoate ion, C3H5O2-. So we know everything in that Ka except for the concentration of the propanoic acid, which would be in the denominator of that expression. So here comes my rice table. I will go ahead and fill in as much as I can in the initial. Now, I don't know the initial concentration of the propanoic acid, or HA. I don't care about the concentration or the information for water. And then we're going to pretend that the reaction has not yet occurred. So initially, the concentration of the hydronium ion, along with that conjugate base, or the propanoate ion, C3H5O2-, are 0. Again, as I mentioned earlier, technically, in pure water, the concentration of the hydronium ion would be 10 to the minus 7. But since 10 to the minus 7 is a really small number, then we can assume that there's no additional hydronium ion formed as a result of this reaction between the weak acid and water, at least not yet, as the reaction has not yet occurred. All right, well, now comes the change in terms of X. So we have minus X for the propanoic acid, and then plus X for the hydronium ion, and plus X for the propanoate ion. So at equilibrium, we have X, and again, we don't know that concentration of the propanoic acid at equilibrium. So there is the concentration of the hydronium ion, or if you don't think that's correct, you can go ahead and check it on your calculator. So if you do 10 to the minus 3.31, which is the pH, then you would get 4.9 times 10 to the negative 4. And based on that 1-to-1 mole ratio, 4.9 times 10 to the negative 4 is also the concentration of the conjugate base, or the propanoate ion. So let's go ahead and plug in everything we know, including the Ka value, into the Ka expression. So I've got 4.9 times 10 to the negative 4, basically squared, in the numerator. In the denominator, I don't know what that concentration is, and then the Ka is 1.4 times 10 to the negative 5. So all I really have to do is a little bit of simple algebra and rearrange that equation. So when I rearrange that equation and solve for the concentration of the propanoic acid, I get, on my calculator, 4.9 times 10 to the negative 4 squared, divided by 1.4 times 10 to the negative 5, and I get 0.017. Now, technically, the change in X is such a small number that when I round off to two significant figures, 0.017 would also be the initial concentration of the propanoic acid. In other words, if you check on your calculator, 0.017 minus 4.9 times 10 to the negative 4, you essentially, when rounding off to two significant figures, you get 0.017. All right, we have now filled in that missing information for part A of the table. Moving on to part B of the table, there's only one thing we have to do, and that's calculate the Ka value. So I'm not going to bother creating a rice table for part B. I will simply write the Ka for HOBr. So there's the hypobromous acid, or HOBr, in the denominator, and the numerator has the hydronium ion along with the conjugate base, the OBr-, or the hypobromite ion. I'm going to plug in what I know. For the concentration of the hydronium ion, that would be 1.4 times 10 to the negative 5 in the numerator. And again, there's that 1-to-1 ratio. I've got my concentration of my acid, HA, in the denominator. So we're assuming that 0.085 is both the initial and the final concentration of HA at equilibrium. So now all I have to do is pick up my calculator and do this math. So 1.4 times 10 to the negative 5 squared divided by 0.085 will give me the Ka value. And when I do that math, I get 2.3 times 10 to the negative 9. So the purpose of question 9 was to show you how you can fill in the missing information for a weak acid. So those are the correct answers to question 9. Now let's take a look at another weak acid in question 10. So here's question 10 involving another weak acid. This is hydrofluoric acid. It says hydrofluoric acid, HF, ionizes according to the equation above. In part A, we have to calculate the pH of a 0.92 molar solution of hydrofluoric acid. So because this is a weak acid, we cannot simply pick up our calculator and take the negative log of 0.92. Again, because this is a weak acid, I think this would be a good example of making a rice table to help you see how to process the information. So where would that 0.92 molar go in my rice table? Well, that's going to go in the initial row. And then I don't care about the water. And we're assuming that this reaction has not yet occurred, so therefore the initial concentrations of the hydronium ion and the fluoride ion would be 0 because HF has not yet reacted with water. So the change would be in terms of X, so minus X, and plus X. And then at equilibrium, we would have 0.92 minus X for the concentration of the HF, and then we have X and X for the concentration of the hydronium ion and the concentration of the fluoride ion. Now, as we have seen so far in this lesson with examples of a weak acid or a weak base, the change is so small in terms of the comparison to the initial concentration of the weak acid or the weak base that we can make the following simplifying assumption. So we can assume that the value of X is so small relative to the initial concentration of HF that 0.92 minus X is approximately equal to 0.92. Now, this greatly simplifies the math that we have to do to solve for X. So we will not be using any fancy equation solver or quadratic equation to solve for X. I'm going to plug in everything I know into the Ka expression. So it's going to look like the following. I've got concentration of hydronium, concentration of fluoride, so that would be X and X. I've got concentration of HF, which is not 0.92 minus X, but based on that simplifying assumption, just 0.92. And I set that equal to the Ka, which we were given in this problem. It's 6.8 times 10 to the negative 4. Let's go ahead and solve for X. So X squared is equal to the product of 0.92 times 6.8 times 10 to the negative 4. So X squared works out to be this number. So 6.256 times 10 to the negative 4. I will take the square root of that value, and this will give me the X, which represents the concentration of the hydronium ion. Now, if this question says, what's the concentration of the hydronium ion in a 0.92 molar solution of HF, then we have our answer. It's 0.025 molar. But we have to figure out the pH, so let's go ahead and take the negative log of 0.025. So the negative log of 0.025 is equal to 1.6. So now 1.60, that is the pH of a 0.92 molar solution of hydrofluoric acid. And I think that using a rice table, as I have shown you in this question, can help you keep track of all of the information. Let's go ahead and move on to part B, which is to determine the percent ionization of HF in a 0.92 molar solution of HF. So what's that ratio for the percent ionization of a weak acid? Well, for the generic acid, it would be concentration of hydronium divided by the initial concentration of HA times 100. Well, what is our specific acid in this problem? It's HF. Let's take the concentration of the hydronium ion divided by the initial concentration of HF and then times 100. So that would be 0.025 molar for the concentration of the hydronium ion divided by 0.92, the initial concentration of HF, times 100. And so the answer to part B is that this acid is 2.7% ionized. Again, that's an indication that HF is a weak acid. It's only partially ionized in solution. Now, as we move on to part C of question 10, it's going to remind you of something you had learned in Unit 7, and that is a comparison of the reaction quotient Q with the equilibrium constant K. Let's take a look at part C of question 10. It says if 50 milliliters of distilled water is added to 50 milliliters of 0.92 molar HF, will the percent ionization of HF in the solution decrease, increase, or remain the same? Justify your answer by comparing the value of the reaction quotient Q with the value of the equilibrium constant Ka. So it's going to be a dilution where we're going to be adding water. And so as we add water, it's going to cause all of the concentrations of the chemicals in the solution to decrease. So let's go ahead and compare Q with Ka. So there's our Ka expression. If we add 50 milliliters of distilled water to 50 milliliters of this HF solution, then the concentration of everything, each species, will decrease by 1/2. So here's my Q expression. 1/2 times the concentration of the hydronium ion, 1/2 times the concentration of the fluoride ion, 1/2 times the concentration of HF, and when I consider how that works out in terms of algebra, I get that Q is not equal to Ka. In fact, Q is equal to 1/2 Ka based on the math. So if Q is less than K, you may have to remember what you've learned in Unit 7. What happens when Q is less than K falls into topic 7.7, which I had presented in an earlier episode of AP Chemistry Review and Practice. So if Q is less than K, then there will be a net conversion from left to right, a net consumption of reactants and generation of products. So if Q is less than K, there is a conversion from left to right or from reactants to products. So I'm showing you an arrow indicating how the equilibrium position would shift if Q is less than K. And so the percent ionization of HF should increase. So the answer to part C is the following. If we do the dilution with water, that will cause the Q to become less than the K for this weak acid. That will cause a shift from left to right, or a net conversion from reactants to products, and the percent ionization of HF should increase. All right, well, those are all of the answers to parts A, B, and C of question 10. Hopefully all that made sense to you. Now let's move on to question 11, which involves a weak base. In this question, we are told that methylamine, which has the chemical formula CH3NH2, ionizes according to the equation above. And we can see from the details of this equation that methylamine is behaving as a weak base. So the methylamine, CH3NH2, reacts with water, and we have the hydroxide ion on the right side of the equation, and we also have the conjugate acid of methylamine, which is called the methylammonium ion. So CH3NH3 plus is that formula on the right side of the equation. So we are given the Kb, 4.4 times 10 to the negative 4, and in part A of this question, we have to calculate the pH of a 2.5 molar solution of this weak base, methylamine. So this question is similar to question 10, and I think let's go ahead and set up a rice table and keep track of what we need to do to calculate the pH of a 2.5 molar solution of methylamine. So here's our rice table. I will put in 2.5 molar for the initial concentration of the methylamine. Again, I don't care about the water. And we will assume that this reaction has not yet occurred, so the initial concentrations of the methylammonium ion and the hydroxide ion would be 0 at this point. The change would be in terms of X, so minus X for the methylamine change in concentration, and then plus X and plus X for the two products. At equilibrium, the concentration of the methylamine would be 2.5 minus X, and the concentrations of the hydroxide ion and the methylammonium ion are X and X. We will go ahead and make that simplifying assumption similar to what I had mentioned in question 10, and that is because the change in X is so small relative to the initial concentration of this weak base, then 2.5 minus X is approximately equal to 2.5. And this greatly simplifies our math. So when we solve for X, we will not need to use any fancy quadratic equation or equation solver. So I'm going to go ahead and put in everything I know into the Kb expression. So that would be concentration of the methylammonium ion times the concentration of the hydroxide ion. So X times X, concentration of the methylamine, 2.5, and that's equal to the Kb, which is 4.4 times 10 to the negative 4. So now I will solve for X. So X squared is equal to the product of 2.5 times 4.4 times 10 to the negative 4. So X squared is equal to 0.0011. I will now take the square root of 0.0011 to solve for X. Now, be careful, because at this point, you might take the negative log of 0.033, and then you think that you're done. You think that you've got your pH because you just took the negative log of a number on your calculator. So watch what happens when I take the negative log of 0.033. So I take the negative log of 0.033 and I get 1.48. Well, this is a weak base. we are expecting the pH to be greater than 7 because this is a base. So if I thought that the final answer for the pH of a 2.5 molar solution of a weak base was 1.48, well, that would be incorrect. So don't forget to pay attention to what you're taking the negative log of. So it's going to be 14 minus the pOH, or in this case, 14 minus 1.48. And when I do that math, I get 12.52. That is a reasonable answer. So this is the pH of a 2.5 molar solution of methylamine. It's not 1.48, it's actually 12.52. So there's the answer to part A of question 11. Now we're going to go ahead and move on to part B of question 11. That's a percent ionization. Here's the generic ratio for the percent ionization of a weak base. So it's going to be the concentration of the hydroxide ion divided by the initial concentration of the weak, and then times 100. So for methylamine, that would be the concentration of the hydroxide ion in solution divided by the initial concentration of the methylamine, and then times 100. So it's going to be 0.033 molar for the concentration of the hydroxide ion divided by the initial concentration of methylamine, or 2.5 molar, and then times 100. So we discover that the methylamine in a 2.5 molar solution of methylamine is only 1.3% ionized. So question 10, in a calculation for a weak acid, that was hydrofluoric acid. Question 11 involves the calculations for a weak base, methylamine. So we're almost done with this packet. One more question remains. Let's go ahead and take a look at question 12, which involves writing a net ionic equation. In question 12, it says, when a sample of solid sodium fluoride, which has the chemical formula NaF, is dissolved in water, the solution has a pH that is greater than 7. Write the net ionic equation for the reaction that occurs to cause the sodium fluoride solution to be basic. Now, with respect to how do you know if something behaves as an acid or behaves as a base, this goes all the way back to Unit 4. So in Unit 4, specifically topic 4.8, Introduction to Acid-Base Reactions, one of the essential knowledge statements is the following. By definition, a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. So we're looking for a substance that behaves as a base. That would be a proton acceptor. So a substance that behaves as a Bronsted-Lowry base is a proton acceptor. So what's going to be the proton donor? That's going to be the water. So not sodium, not fluoride, but H2O. So the water molecule will behave as the proton donor. So it loses H+, and then something in the sodium fluoride is going to behave as the proton acceptor. So which particle, the Na+ or the F- in sodium fluoride, is more likely to behave as an H+ or a proton acceptor? Well, I think it's unlikely that Na+ would accept H+ because they're both positive. So I would think it's more likely that the fluoride ion will behave as a weak base. And you might already know this because HF was something I had mentioned earlier in this lesson. So if HF, or hydrofluoric acid, is a weak acid, then its conjugate base, F-, behaves as a weak base. So there's the arrow I'm showing you in indicating a new bond is going to be formed between the F- and the H+. And then when that bond breaks between the H and the O, it's going to form the hydroxide ion. So the products of this reaction between the F- or the fluoride ion and water would be a molecule of HF and then the hydroxide ion. So the F- reacts with water and it produces a molecule of HF and the hydroxide ion. So there is our balanced net ionic equation for the reaction that would show why sodium fluoride behaves as a base. The fluoride ion, acting as a weak base or a proton acceptor, reacts with water to produce HF and the hydroxide ion. All right, well, question 12 is the last question in this packet. So now it's time to move on to the part of the lesson where I give you advice to help you avoid common mistakes. My first piece of advice is if you need more information for topics 8.1 to 8.3, then you can check out this video, which is linked in the video description area. And you can find it on my YouTube playlist that's organized by AP Chemistry CED units. My next piece of advice is what I normally say during this point in the lesson. Read the question carefully and make sure you are answering the question that is being asked. This is especially true when you're dealing with the difference between pH and pOH, or the difference between the hydronium ion concentration versus the hydroxide ion concentration. So be careful with that. My next piece of advice is to always show your work for your calculations so you can make sure to earn credit for your responses on the free response section of the AP Chemistry exam. Now, with respect to topic 8.1, if you have a question that refers to pure water, but you're at a temperature other than 25 degrees Celsius, the following is true. The pH is equal to the pOH for a sample of pure water, but that value will not equal 7. The sum of the pH plus the pOH is equal to the pKw. Again, for pure water, pH equals pOH, but that pKw will not equal 14 if you're at a temperature other than 25 degrees Celsius. And the concentration of the hydronium ion is equal to the concentration of the hydroxide ion in a sample of pure water. And you can just take the square root of the Kw, but you are not going to get 1 times 10 to the negative 7 if you're at a temperature other than 25 degrees Celsius. So watch out for that. All right, my next piece of advice is that some useful equations, such as the 10 to the minus pH to get you the concentration of the hydronium ion, or 10 to the minus pOH will get you the concentration of the hydroxide ion, or this equation involving the percent ionization of a weak acid, or this equation involving the percent ionization of a weak base. These are useful equations, but they are not listed on the AP Chemistry equations and constant sheet, so be aware that these are equations that you should be able to know and use, but you won't find them on the equation sheet. My next piece of advice is to take care to avoid mistakes such as the following when calculating the pH of a strong base. So in this example, the student had to determine the pH of a solution, and it was 2.8 times 10 to the negative 4 molar for the concentration of sodium hydroxide. So the correct answer would be take the negative log of 2.8 times 10 to the negative 4. Now that would get you the pOH, so 3.55 is not the final answer. 14 minus the pOH, so 14 minus 3.55 gets you 10.45. Now that is the correct answer. So here are two examples of a student mistake and why that's incorrect. So what did this student do wrong? They stopped at 3.55, and that was what they wrote down as their final answer. So the student used the hydroxide concentration. They took the negative log and they got the value of pOH, but they called that answer the pH, which is incorrect. Now, this student did something that you might actually not see at first, like what they did wrong. What they did was something that you would normally use when you're calculating the number of moles. So they did volume. So the beaker contains a 50 milliliter sample, and so they turned that into liters. They multiplied the volume in liters times the molarity, and they got 1.4 times 10 to the negative 5. And then they finished their calculations for pOH and pH, and so they got 9.15 for their final answer. So what did they do wrong? They used volume and molarity to calculate the number of moles. And they calculated the pOH and the pH by taking the negative log of the number of moles instead of using the molarity. So that is a mistake that I want you to avoid making on the AP Chemistry exam. So we take the negative log of the concentration, not the negative log of the number of moles. All right, my next piece of advice has to do with a weak acid. So take care to avoid mistakes such as the following when calculating the pH of a weak acid. So here is a weak acid. This is called formic acid. It has the chemical formula HCOOH. We're given the Ka value. It's 1.8 times 10 to the negative 4. And we have to calculate the pH of a 0.25 molar solution of formic acid. So I made a rice table that 0.25 minus x was approximately equal to 0.25, and that's because the value of x is much smaller than the initial concentration of the acid. So I have x squared divided by 0.25 is equal to the Ka, which is 1.8 times 10 to the negative 4. Then I solve for x, so I did x squared is equal to 1.8 times 10 to the negative 4 times 0.25. And then at this point, I got 4.5 times 10 to the negative 5 on my calculator. I took the square root of that number, and I got 0.0067 on my calculator. And then I took the negative log of that concentration of the hydronium ion. So I solved for x, took the negative log, and I got a pH of 2.17. Now that is the correct answer. So 2.17 is the pH of a 0.25 molar solution of this formic acid based on the Ka value I was given. Now, here are the mistakes that I would like you to avoid. So, first example of a student mistake. They got a pH of 5.01. Well, what did they do wrong? They used natural log on their calculator instead of the log base 10. This student got a pH of 0.602. What they did wrong was they assumed it was a strong acid, so they just took the negative log of the concentration of a weak acid, and that's incorrect. This student did take the negative log, but they used the wrong value. They took the negative log of the Ka. So what they actually calculated was the negative log of the Ka, or the pKa, instead of figuring out the pH. And then what this student did wrong is they got so close to the x squared is equal to 4.5 times 10 to the negative 5, which is correct, but they forgot to take the square root of that number to solve for x. So they took the negative log of a number that was actually x squared instead of x. Here is another example of a student mistake. So they have x squared is equal to 1.8 times 10 to the negative 4, which is actually the Ka. So they either neglected to use the 0.25 molar in their setup, or they incorrectly assumed that the concentration of the weak acid was 1 molar. So there's no 0.25 molar used in their setup, so they got the wrong pH value. And here is another example of a student mistake. They accidentally divided by 0.25 instead of multiplying by 0.25. So that mistake was effectively an algebraic manipulation mistake. So all of these mistakes that I'm showing you are examples of the kinds of things that we would see students do at the AP Chemistry reading. And so I'm just calling your attention to these mistakes in the hope that you won't make those mistakes when you're taking the AP Chemistry exam and you're solving a weak acid problem. All right, my next piece of advice is to make sure you understand the difference between a strong acid and a weak acid. So as you know, a strong acid is 100% ionized in water, whereas a weak acid is only partially ionized in water. Now, with a weak acid, if you know 2 of these values, you can calculate the third. So we have the Ka value, the initial concentration of the acid, and then we have the pH, or the concentration of the hydronium ion. So what I will do is show you a situation where if you know 2 of these values, you can calculate the third value. So suppose you were given the following situation. You have the Ka value for a weak acid. I'm just making up a value of 1.8 times 10 to the negative 5. And if you know the initial concentration of the weak acid, so for example, let's say it's 0.50 molar, the question might ask, what is the pH of a 0.50 molar solution of a weak acid? And again, the Ka value would be given. What you would do is you would plug in x and x into the numerator. You would plug in 0.50, the concentration of the weak acid, into the denominator. You would set that equal to the Ka value, which is 1.8 times 10 to the negative 5. All you have to do now is solve for x and then take the negative log of that value to get the pH. So if I solve for x, it works out to be 0.0030 molar. I'm going to go ahead and take the negative log of that number, and I get a pH of 2.52. So again, I knew two of those values, and I could solve for the third. Let me go ahead and switch it around. Now, suppose you're given the Ka and you're given the pH. So the question might look like the following. A solution of a weak acid has a pH of 2.52, and again, the Ka value is given. What is the concentration of HA? So if we know two of these three quantities, let's calculate the third that we don't know. So the 10 to the minus pH would be 10 to the minus 2.52. And so I got 0.0030 molar for my concentration of the hydronium ion. I'm going to plug that into the numerator of the Ka expression. And based on that 1-to-1 mole ratio between the hydronium ion and the conjugate base of the weak acid, I've got 0.0030 molar squared on the numerator part. I don't know the concentration of HA, and I set that equal to the Ka value of 1.8 times 10 to the negative 5. A little bit of algebra, and I could solve for HA, and when I do that, I get 0.50 molar for my concentration of HA. So again, you're given two of the three values, and you can solve for the third. Now, suppose that we don't know the Ka value. The question might look like this. A solution of 0.50 molar HA, so a weak acid, has a pH of 2.52. What is the Ka value of this weak acid? So there's my Ka expression. I've got 0.0030 molar for the numerator for both the hydronium ion and the A- because I did 10 to the minus pH, or 10 to the minus 2.52. So there's my numerator. And then my denominator is the concentration of the weak acid. So I know everything in the Ka expression. I plug in 0.0030 squared divided by 0.5 into my calculator, and I get that the Ka is 1.8 times 10 to the negative 5. So just to show you some examples of if you know two of these three values, you can calculate the third value. Now, as you're watching this video and you're wondering, is there a similar situation for weak bases? Yes. Let's go ahead and take a look. A strong base is 100% ionized in water, whereas a weak base is only partially ionized in water. And with a weak base, if you know two of these three values, you can calculate the third value. And the three values would be either the Kb for the weak base, the initial concentration of the weak base, or the pH, or the pOH, or the concentration of the hydroxide ion. So suppose we have a weak base. I'll just make up a Kb value of 1.8 times 10 to the negative 5. And let's suppose we know the initial concentration of the weak base is 0.50 molar. So you might see a question on the AP Chemistry exam that says, what is the pH of a 0.50 molar solution of a weak base where the Kb value is given? So you've got your Kb expression. You can plug in X and X in the numerator because we don't know those concentrations. You can plug in 0.50 molar for the concentration of the weak base. You can set that equal to the Kb. Go ahead and solve for X, and then you will take the negative log, but watch out. So I'm going to go ahead and solve for X. So X squared is equal to 9 times 10 to the negative 6. This is now time to take the square root of that number. Aha, watch out. If I take the negative log of 0.0030 molar, this will not get me the pH, this will get me the pOH. So if I take the negative log of 0.003 on my calculator and I get 2.52, I'm not done yet. 2.52 is not the pH of a 0.50 molar solution of a weak base. I'm expecting a pH greater than 7 for a weak base, not less than 7, greater than 7. So the pH would not be 2.52, it would be 14 minus that value. So watch out for that. So the pH could be, in this case, 11.48, and that's reasonable for a weak base. Now, suppose you were given the Kb and the pH, and you had to solve for the initial concentration of the weak base. So it might look something like this. A solution of a weak base has a pH of 11.48. What is the concentration of that weak base? So the first thing I will do is remember that pH and pOH are not the same thing. So 14 minus 11.48 is equal to 2.52. Now the concentration of the hydroxide ion in solution is 10 to the minus POH, so 10 to the minus 2.52. I will put that number, 0.003, into the numerator, and it's going to be the same as the concentration of the conjugate acid Hb+. So 0.003 squared divided by some number I don't know is equal to the Kb of 1.8 times 10 to the negative 5. A little bit of algebra to solve for the concentration of that weak base, and I get 0.50 molar. And again, as a final, what if you know two of these three values? What if you don't know the Kb, but you know the initial concentration of the base, and then perhaps the pH? The question might look like this. A solution of 0.50 molar, a particular weak base, has a pH of 11.48. What is the value of Kb of this weak base? Let's go ahead and remember that pH and POH are not the same thing. So 14 minus 11.48 is a POH of 2.52. 10 to the minus 2.52 will give me not only the concentration of the hydroxide ion, but also the concentration of that conjugate acid Hb+. So my numerator would be 0.030 squared. My denominator is the concentration of the weak base that I was given. And when I plug in those numbers into my calculator, I get that the Kb is 1.8 times 10 to the negative 5. So just to show you that whether it's a weak acid or a weak base, if you know the K value, the initial concentration of that weak acid or that weak base, and you know the pH or the POH, you can solve for the third value if you know two of those three. All right, well, now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 8.4 and 8.5. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.